Okay, chapter 15, structural geology. Like I think I've mentioned in class, this is about rock formations and rock beds bending and folding and breaking, and how we sort of talk about that, the terms that are used, and how we can measure these things. So, we'll talk a little bit about an introduction. We'll talk about the difference between stress and strain. We'll talk about strike and dip, which is kind of how we measure rocks. We'll talk a lot about folding and the different terms about the different shapes we see in rocks and what we can see. This will be kind of a big break in here. So if you want to go through some of this and then watch some of it later on, this is kind of a good stopping point. But after this, we get into faulting, and then actually, I don't even talk about unconformities. This is chapter 8. So, structural geology has to do with the shape of rock layers, how they are oriented, and why, and why we care. So we'll talk a little bit about that. So it's the arrangement of these rock layers. Which way are they bending? Which way are they dipping? Which way are they pointing? The relationship to each other. But generally it's just which way are these rocks oriented. And we're mostly looking at layers of rocks here. Mostly we're talking about sedimentary rocks. We could be talking about layers of igneous rocks or even metamorphic rocks, but typically, it's kind of reserved for sedimentary rocks, mostly because sedimentary rocks are the majority of the surface of the Earth. Why do we care? Well, a lot of it has to do with resources. There's been a lot of study that goes into structural geology because oil and gas ends up becoming trapped in the bends in these rocks or where they're broken. And you have to understand a lot about the permeability and porosity, which we've talked about, of certain rock layers and how that might trap oil and gas. So if I've got a layer of, let's say, sand, which is very porous and very permeable, and it's kind of faulted on one end and butting up against a shale or something that's not very permeable, that can kind of trap oil in that one spot where it kind of bumps up against an aquitard, right? Something that where the flow, it can't go anywhere, so it gets trapped. Same sort of thing with groundwater. Oil and gas moves around in permeable layers. Well, so does groundwater. Also, ore minerals. If we go down to the southern part of this state, you can go quartz mining. Those quartz crystals are trapped in the broken parts of the rock down there. Also, we care about it with mass wasting. If you've got rock layers that are kind of tilting towards you, then the mountain can sort of has a much easier time of sliding down on your head. But anyway, those are just a few examples. Let's kind of get into some of the meat and potatoes of this stuff. Stress versus strain. So, stress is the force applied to a body. If I'm pushing against you, I'm applying stress to you. If I push against this desk I'm sitting in front of, I'm applying stress to it. There's different types of stress. There's compressive, tensional, and shear stress. Compressive stress will shorten and thicken a rock body. We find this at convergent boundaries. It's not an accident that we have compressive, tensional, and shear stress here. Compressive is like your convergent boundaries, tensional is like your divergent boundaries, and shear stress is more your transform boundaries. So tensional stress, we'll find it at divergent boundaries. This will thin and lengthen rock bodies. It will thin and lengthen the crust. And it can also provide a little bit of regional uplift. That's because you're sort of, if you thin out a material, you make it lighter. I think I've used the boat analogy before. If you put a whole bunch of stuff into the boat sinks. If you take a bunch of stuff off the boat rises up. So if we've got Earth's crust, if we got a bunch of light stuff on top of it, and we thin it out, the underlying part of that crust may actually rebound up a little bit and create a little bit of uplift. That's a little bit advanced for this class, I think, but just want you to know that it can cause this, and it may have something to do with some of the geology we see around here. So compressive stress will shorten and thicken. Tensional stress will stretch things out and also make it thinner, or it can even break it. Shear stress is something we'll see at a transform boundary, also a subduction zone. So as a piece of oceanic crust is getting subducted underneath the continent, it can kind of be, the top of it can be sheared off by the continental crust. So what about strain? Well, stress is the force applied to a body. Strain is the actual change. So you can put a lot of stress on your ankle, but if you strain your ankle, you've actually done some damage, right? I think strain is used in talking about hurt ankles, right? So the strain is the actual change. It's the result of the stress, and you can actually get deformation. You can get change. So there's 3 different types of strains. There's brittle, elastic, and ductile. Brittle is the rock breaks. If we put too much stress on it, it'll break, and that's brittle strain. This typically happens to rock that is cold. It's nice and settled. The rock we see at the surface of the earth is technically cold for the most part, and it will act in a very brittle manner. Elastic rocks can bend and then kind of return back to their shape. This is a little bit rare, but we'll see it a lot. Actually, when we talk about tsunamis, which we'll talk about in the next chapter, that's the result of an elastic rock, where you may bend rock and maybe part of it breaks and then the other part of it snaps back. That's because it has an elastic reaction. Then ductile is where, you can probably guess at this point, you bend it and it bends permanently. We see this happening to rock that is softer and hotter. So rock that is buried deep beneath the surface, several miles down where it's quite warm, that will actually bend permanently, kind of like silly putty or something, instead of breaking. So it happens deep in the crust. We can see this rock if it ever makes it up to the surface. So if we have a mountain building event, we have a couple of continents coming together, they push up some mountains, or they push up a lot of the ground into mountains, and then within those mountains we can see rocks that have been ductily formed, and they're kind of bent and folded. So the type of stress we get is determined by plate boundaries, right? If we're at a convergent boundary, we're getting compressional stress. If we're at a divergent boundary, we're getting tensional stress. And then the type of strain, instead of being determined by plate boundaries, it's kind of how deep you are in the earth. The deeper you are, the more likely you are to get ductile deformation. But if you're shallower, you'll get more potentially elastic or brittle. So let's talk about how we sort of measure rocks that have been deformed. So in general, when sediment's deposited, it's deposited horizontally, right? We see that in the rocks around here in northwest Arkansas. Most of our rocks are very, very flat lying. If you go look at all the sand being deposited out off the Gulf of Mexico, it's starting out being nice and flat and horizontal. However, over time, through tectonic forces, you can start to bend these things or tilt them over. And when that happens, we need a way to describe them. Which way are they tilting or dipping? Which way, how are they bending? And so those are going to be the things we talk about. So first off is strike and dip. So take a second to take this picture in. What do we see? We've got sedimentary layers that are tilting this way. We'll say they are dipping this way. Excuse me. And we also have, here's a north over here, and we have this thing called strike. So this is the line I really want you to pay attention to in this picture. And also there's water here. The water is here just to show us where a horizontal plane is. This is a flat plane. It should go all the way through here. And the strike is where that flat plane of water meets this layer of rock. And when that top of that flat plane of water meets that layer of rock, there'll be a line where it meets it, just kind of like there's a line of water on the beach, right? Although usually it's waves moving back and forth, but if this water is still where it meets this shale here, it creates this line of strike. And this line of strike is pointing towards the north and the south. So we'd say this layer, these rock layers, are striking north or striking south. And like I said, it's at the intersection of that bed of rock and just an imaginary horizontal plane. So here are some rock layers. What's kind of nice is we've got sand here that's sort of creating our horizontal plane, right? The sand may not be there always, but here it is, and we can see that the strike is generally heading in this direction. So this horizontal plane ends up meeting these dipping rocks, and that strike is off in this direction, going away from us and towards us. Strike is always measured from the north. When we get into class, I'm going to pull out a compass, a geologic compass, and I'll kind of show you how this works using one of the tables. But we measure it from the north, and there's a couple of different ways to do it. So here's a person that's doing it. They've got a compass. They see this rock layer here. They're kind of laning the compass so it's nice and flat. There's a little level in there with a little bubble. And they're lining it up next to the rock to try and figure out the strike. Now this is a lumpy rock, so it's a little bit hard to tell. But they're just trying to do their best estimate and sort of determine that the strike, you'll notice the way their compass is, this whole rock layer should be striking in this direction. We can sort of see that up here. We have all this sediment that's kind of loose. It's also touching the rock up here. And we can kind of see that direction of strike is generally in this direction. There's a couple of different ways to measure strike. The first way, and actually this is not the way I prefer to do it, but the first way is you'll kind of use three components. You'll say it's striking towards the north, and you'll use some sort of degree angle, and then you'll say whether it's east or west. So I can come back here to this photo and say, okay, this rock is striking towards the north, and it looks like it's a little bit, if north is straight up this way, is going this way, let's assume north is so, straight up. We could say this is striking to the north and a few degrees to the west. Right, so it's striking towards the north and maybe 10 degrees to the west. Alternatively, you could just say it from 0 to 360 degrees. You don't need this north, this many degrees west or east. You can just look at your compass, see which way the arrow is pointing and what number it's pointing to, and say, okay, this is striking this many degrees. So, moving away from strike, dip is how steep the bed is dipping. We can sort of think of it as like the steepness of a roof. So if this roof is our rock bed, how much is this roof dipping? If horizontal is 0 degrees, then this roof is dipping 45 degrees. If it were shallower, maybe it'd be about 35 degrees. So there's two components to how we measure dip. One is the angle, and the other is direction. So this rock bed is dipping 30 degrees from the horizontal, and it's dipping towards the west. Dip is always taken perpendicular to the line of strike. You want to try to find the maximum dip of a bed. So honestly, we don't worry too much about the direction of the dip. We say, east, west, north, south, because the strike really tells us the orientation of that bed, and then the dip is just the maximum sort of angle that it's dipping. And there's two components. There's the degree and then sort of the direction. Is it northwest, northeast, south, east, west, north, whichever. So we can write this on a map. So let's pretend we've got a geologic map. Here's a map. And there's these rocks we see at the surface of this map. There's limestone, sandstone, and shale. And then there's all these little indicators, all these little symbols. These symbols are telling us the strike and the dip. The strike is just where it's pointing. Where this long line is pointing is the strike. And here we have a thing over here. This tells us it's north. So these things are striking north and south. If we said it was striking south, that would be just as good as saying it's striking directly north, because it's sort of a two-way line. So this is striking north and south, and the dip is 30 degrees. So these rocks are actually dipping down into the ground this direction at 30 degrees. And so let's cut into this, right? Let's take a cross section. So here, let's cut into this. Here's A, here's B. We're going to cut into this map. We're going to cut down several yards, and then we're going to turn this rock on its side, and we're going to put it down here to see what it looks like underneath the ground. Okay, ready? Boom, there it is. So from A to B, now we're looking into the ground. This is no longer a map view. And we know the dip is 30 degrees. And so here's what that would look like underneath the ground. So underneath your feet here, underneath this sandstone, you go down a little ways into the ground, and you're going to end up coming into contact with that limestone. I know that because this is striking this direction, and it's dipping 30 degrees. What if I've got crazy things happening where these symbols are kind of pointing away from each other or pointing towards each other? Well, when we see this, it means there's folds one way or another. So let's start talking about folds or folding rocks. Folds are basically bends in the layers of rocks. They have been bent, they have been deformed ductily. It is caused usually by compressive stress. And again, ductile deformation. So I say usually, but for all intents and purposes, it's compressive stress. And again, ductile deformation occurs deeper in the crust. So here is some folding. This is a whole lot of folding. You can see there's a little person up here, so they're about 6 feet tall, so that gives you an idea about how much this is. But you can see these folded layers, right? You can follow these beds along and kind of how they're folded throughout this. You see it? So these rocks have been squished and they're folded up, just like if I squished a rug, pushed one end of a rug, and somewhere in the middle of the rug there'd be a fold. Same thing. Here's another version. There's actually some topography up here. This is the surface, and this is kind of down along the side. This is another cross section. But we can see there's a big fold in the rocks here. And that is a special type of fold called an anticline. And there's two main types of folds. There's anticlines and synclines. And anticlines have an arch shape to them. They are arching upwards. And the limbs, what we call the limbs on the sides, they will dip away from the middle, or dip away from the axis. So here's an anticline. and the limbs on the side, they are dipping away from the middle, from the hinge, from the axis. See that? See how these things are dipping away? Dipping away? If these were like a slide and I sat on here, I'd slide away. Another example, so let's break this down. Anticline, there's the bottom part, so that's a syncline, that's the opposite, but here's the limb, here's kind of the hinge in the middle, so this is an anticline right here. There's another anticline on the other side, but these limbs are dipping away from the middle. Here's a small anticline. It's kind of not symmetric. The hinge is right here. But again, both sides are kind of dipping away from the middle. Now there's a syncline, which you've already seen a couple of. Instead of being arch-shaped, it's U-shaped or trough-shaped. And it's a downward fold, and then the dips point towards the axis. So here's a syncline. Ignore the topography. But here's a syncline. And these layers are dipping towards the middle. So if I sat on this little dark layer here, I would end up sliding towards the middle. So here's a syncline. Same image as before. We would end up sliding towards the middle. And yes, I said this was an anticline. This is a syncline. You notice this part in the middle can be part of either. But if we're looking at just this, we'd say that's an anticline, and we'd say this is a syncline. So let's take an anticline and a syncline, kind of put them together, and let's look at how this would end up looking on the surface. So take a second to kind of look at these layers and where they come up here on the surface. So there's a shale that's kind of up here in the middle. There's a sandstone that's kind of showing up over here and showing up over here. And there's an oranger sandstone that's showing up here in the middle. And there's this other sandstone that shows up on the other side of the surface. So if we were to map this out and try to draw these contact lines in, this is what the map would look like up here on top. And we could go around with our little compass as geologists, and we could measure the strike and dips of these rocks and put these symbols on there. So the strike would be this way, and we could measure the dip, and we'd see that this layer is dipping about 25 degrees in this direction. And on the other side, it's dipping in the opposite direction, about 30 degrees. And there's this hinge in the middle. This little symbol just kind of tells me that's an anticline. It's dipping away from the hinge. And over here, we actually have a syncline. So we're dipping towards the hinge. So this little symbol tells me it's a syncline. And this little thing just tells me in the middle that there's no dipping. It's just flat. So hopefully you can stare at this for a little bit and try to wrap your head around it based off looking at these symbols and kind of what they mean and how I can take a map. I could block all this other stuff out and I could look at just this map and I should be able to draw all this stuff underneath out just based on these symbols on the map. So what about the age of the rocks? Well, in an anticline, the rocks in the middle are older. In a syncline, it's the opposite. The rocks in the middle are younger. Let's look at that. So we have a syncline. The rocks in the middle are younger, right? Because they're sitting on top of these other ones. Versus an anticline, you've kind of eroded away these upper layers. The rocks in the middle are older. So if we were to walk away from the middle of this syncline, we'd be on these old rocks, and then we get to younger rocks and even younger rocks. Versus the other way, if we start on the syncline, we're starting on the younger rocks, and then we're moving to older. All right, it gets even crazier. Folds can also plunge, which basically means the entire fold can also be dipping. I'm not expecting you guys to sort of remember this stuff or try to visualize this stuff later on. I'm just trying to introduce to you how complicated this stuff can get. So here it is. Here's similar folds again, but instead of just being really simple and kind of flat lying, the folds themselves are dipping or plunging towards us. See that? And I wish I could kind of show you my hands and kind of tilt this, but you can see over here, this is kind of showing you what's going on over here on the side, that this stuff is now dipping towards you. So not only do you have these wavy folds, but you're also dipping them towards us. And it'll end up creating these features on the surface. So I'm going to invert this just to kind of show, because I'm going to show you a photograph of what this looks like in the real world. But first I'm going to invert this picture. Boop. So now we see these plunging folds this way, and now let's look at it in the real world. So there you go. Let's go back again, and real world. So what do we see? Well, you can kind of look down here, and you'll notice that these rock layers are actually kind of dipping in this direction. And if you can't see that, that's fine. It just, you have to take time to look at this stuff, and maybe since I've actually been out and mapped out places like this, it's a little bit easier for me to see. But these rocks down here are the same rocks that are over here, and they've just kind of lost their tops. And the same thing with this ridge. This ridge would connect up with this ridge over here. So just like in this picture, this is actually a little bit inverted, but this ridge would end up connecting over here. But we can see that this plunging anticline would end up meeting at this point up here. That's what that would end up looking like. So there's a big anticline. How do I know it's an anticline? Well, really, I don't. The only reason I know it's an anticline here is because of this symbol. It's telling me the dips are dipping away from me, so this must be an anticline. Plus, I can kind of see it in this photo. But there it is, a plunging anticline. So, folds can also, not only can they be plunging, but they can also be asymmetric, overturned, and recumbent. And what's that look like? Well, basically, some of these folds we're looking at are just very symmetrical, nice and even. In the real world, they can be quite asymmetrical at times. But if you tip them over too far, we'll call them overturned. So you'll notice that this layer right here is almost straight up and down. If we kick it over just a little bit to where it's kind of starting to be upside down, then we'll say it's overturned. So this layer has been overturned. And if you kick the whole fold over to where it's horizontal, we'll say it's recumbent. So here's a recumbent fold up on a mountaintop. It's completely sideways. See that? So is this an anticline or a syncline? I don't know, it's sideways. It kind of depends on which way was up. If this way was up originally, then I'd call this an anticline. But I really can't tell. I'd have to get closer to these rocks and figure them out. But which way was up when these were deposited, I can't tell from looking at this picture. So, this is kind of that pause point. You want to take a break, go get some coffee, some tea, or an adult beverage, or whatever you want. This is a good break. Let your brain kind of compile this, because now we're going to move into a whole bunch of other terms dealing with breaking rocks. So, faults. First off, there's something called a joint. And a joint is not a fault. It's a break in the rock that hasn't become a fault yet. Joints will happen when there is brittle deformation, so it's where rocks break. It's where they fracture. It's an area of weakness where they break, and they're cool because water can flow through these joints. Sometimes hot water can go through there, and you'll get ores being deposited, or you'll get crystals growing if you're down in near the hot springs area. And also it's a way for the rocks to kind of start weathering. So Here's a picture. There's a whole bunch of jointing going on all throughout this picture. You see all these little lines, all these broken areas that are kind of running this way and running this way. Those are all joints. We saw a lot of joints when we went out and looked at the rocks on the side of the road, assuming we've done that already. So a lot of times when you're just, again, driving alongside the road, you see breaks in rocks. Normally those aren't faults. Those are just, they're all joints. So all these little lines through here you see throughout this, they're all joints. This is maybe a big joint. Maybe this could be a fault. I don't know. It's hard for me to tell. But I'd probably just call that a joint. Now, a joint where there has been movement is called a fault. And is where the rocks have been displaced, they've moved relative to each other, and it's where it's broken. So here we have a couple of faults. Can you see them? The fault here is that this guy's shorts are way too short, and that's the fault. No, I'm just kidding. The fault here, there's two of them. There's one right here, there's one right here. And you can see this dark layer right here, it's kind of like a double layer. It should be connected up down here to this double layer. And so there's been movement along this line, along this break. Here's another fault. Can you see it? There it is. So this darker layer was once connected up to this darker layer down here, and there's been movement along this fault. This side has gone up, and this side has gone down. Here's another one. Can you see it? A little bit harder, but there it is. These layers used to be connected to these layers. You can correlate that. You can see those, how similar they are. And how this stuff right here used to be connected to this stuff. A different type of fault. This is on the surface, but you can see how in this farmer's field, these rows used to line up. That's a fault. Here's one that's a little bit messy. We even have some ductile deformation here, so when this happened, you're probably pretty deep in the earth. So here we actually have what's called a fault zone. And let's kind of draw it, and you'll get an idea of what's going on. So there that is. So this side's moved up just a little bit relative to this side. And these rocks, this rock layer right here, should be connected up with this rock layer over here. So a little junked up, not as clean as the other photos, but still a fault. There are different types of faults. There's two big categories. There's dip-slip faults, and there's also strike-slip. There's a bunch of different dip-slip faults, and there's also these terms we need to talk about real quick to kind of help us characterize these different types of faults. So these two terms, there's what's called a hanging wall and what's called a footwall. So with a hanging wall, imagine you're standing on a fault. Imagine you're like super, super tiny and you're like just sitting there standing on the fault. The rocks above you are the hang wall. The rocks below you are the footwall. So the rocks you'd be standing on are the footwall, good name. Rocks above you are the hang wall. This is one of those areas in geology where the names actually make sense and they're good names. Yeah, so let's look at some of those. So we'll look at some of those by looking at some of these different dip-slip faults. There's normal dip-slip faults, there's reverse dip-slip faults, and there's thrust. These two are very similar, but this one's different. With a normal fault, the hanging wall moves up and the footwall moves down. What do I mean by that? Let's take a look. Let's take a look at this piece right here. So we have a fault. And remember, if you're standing right here, the rocks, so you're standing on the fault, the rocks above your head are the hang wall. The rocks below you are the footwall. So with this normal fault, the hang wall has gone down, the footwall has gone up. Hang wall down, footwall up. See it? Hang wall has gone down. There's the arrows to help you out. You can see these layers, that this used to be connected up here, so this has gone down, and this has gone up. Same sort of thing over here. And again, we can bring it down here. Normal faults are caused by tensional stress. So we're pulling these rock layers apart, and the middle part has sunk down. And so these are normal faults. The hang wall has gone down. The hang wall has gone down. The footwall has gone up. It's more important to visualize this from tensional than really just memorizing these terms. My hope is that I could tell you, like, draw tensional faulting and you could draw something like this. Or draw a normal fault and you should be able to draw something like this. So here's one in real life. You can see these layers. These layers used to be connected up here. This layer used to be up here. This layer used to be up here. And same thing on the other side. And there it is drawn out to kind of help you. So the hang wall has gone down. So if we stood here on this fault, hang wall's above our head, it's gone down. Footwall, gone up. So I can look at this and be like, oh, there was tensional stress. This was pulling this way and this was pulling this way. And this outside parts ended up falling down. And that's everything I just said. With reverse faults, it's the reverse. The hang wall's up, the footwall's down. It's not tensional stress, it's compressional stress. So we compress it, and there's a fault, and the hang wall goes up, and the footwall goes down. See that? This is just showing it if you erode the surface off, which typically is what happens. You know, the area will be flat, but you'll still have these faults that have happened in the past. So again, hang wall up, footwall down, happens from compressional stress, usually found at convergent boundaries. What about thrust faults? Oh, here's another picture. Sorry. So real life, there's the fault, hang wall up, footwall down. Hang wall up, footwall down. And it kind of makes sense if you think about the tension. You're pushing this together, you get a fracture, one part's going to go on top of the other part. So thrust faults, and I will probably forgive you if you get these two mixed up because I get them mixed up. They're the same as reverse faults, they're just at a really low angle, and they're important because they'll happen regionally. So these faults won't just happen, you won't just see them in the side of the road, they will continue for miles and miles and miles and miles. So here's a thrust fault. So much lower angle, so you can kind of see this has this angle. This is at a much lower angle, and so we give it a different name because it's kind of this regional feature that you'll see. And so here's some compressional stress, and you're kind of building these mountains because you have this convergent boundary. And this fault, this thrust fault, will continue regionally all the way along this whole kind of mountain chain. So that's kind of, we give them their own little category. And here's one in real life. You can see the fault is right there. These layers are bending, and who knows how long this stuff has traveled. I don't know if these layers actually go to these layers. These layers could go to layers that are way down off the screen here somewhere. So there could be a whole bunch of offset. What about strike slip? So you can have two types of strike slip faults. You can have right lateral and left lateral. They're there's a really easy way to remember this, and it's just to use your imagination. So let's show you a little strike slip fault. Here's a couple of them. If I'm standing right here, so these kind of happen into the ground, right? It's like that transform boundary, one that's just sliding next to each other. This is what you see in California with the San Andreas fault. But if I'm standing right here and looking over here, if I'm standing right here and then boom, an earthquake happens and this fault shifts, this side of the land is moving to the right. So it's a right lateral fault. And the same thing, if I were standing on this side and looking this way, this rock would be moving to my right. So this is a right lateral fault. And this is also a right lateral fault. But if we were to swap it, it would be a left lateral fault. And so here's one, we already looked at this picture, but this is a strike slip fault. And this is the opposite. This is a left lateral fault. So if we're standing here, the land on this side actually moved to the left. And it wasn't to the right. It's to the left. So right lateral fault, left lateral fault, pretty simple. Here's another one. This one's a little bit hidden, but there's a fault that goes along here. And we can kind of tell the offset because you can sort of see these little ravines in here and how they're getting pulled over. You see that? So the topography kind of tells us what's going on with this. So you see these bends. And that is it for this chapter. I encourage you to rewatch it if you couldn't wrap your brain around it. Wake up in the morning to watch some of this over again. The folding can be a little bit complicated in how that works. In class, we will kind of go over a little bit of this. I'll probably do a little bit of a review, but then we'll actually start looking at some of the maps and putting some of those symbols on it, and I'll ask you to, okay, draw what it looks like underneath the ground based on what we see on the map. And that's all for now.